Okay, a small follow-up subject. I was talking to Markus Heinrich and he explained to me a couple of things. In previous sessions, we were more or less right about the center, but we were not right to freak out so much. Yeah, it's actually a bit simpler than we thought, and it's not a big problem. So basically everything we were saying, it more or less checks out, and if you continue with the formulas, everything works out nicely. But I want to say something more about the irreps. Okay, so I was avoiding this a little bit in my presentation, but we had the statement of Schur's lemma saying that if we are averaging over an irrep, so let's say we construct this H, I think H0 in the notation of Wikipedia, and then we have G in some G, which is an irrep, and we are considering G minus 1, probably here it was, then this is either 0 or identity divided by the trace of H. Okay, and then we had the situation that we consider the dephasing channel. And the dephasing channel was basically, let's call it delta D for dephasing. We take some matrix A, and we considered A to be a 2x2 matrix, let's say. And basically what we said, it would be the identity A plus conjugating by Z. That was our idea for the channel. And then we check different things. So for example, delta of identity is identity. Maybe we do 1/2 somewhere. Or let's not do 1/2. Let's do times 2. Delta of Z, what is this? This is Z plus Z to the power 3. So you can compute while I'm writing the other stuff. X plus ZX here. And delta of Y plus ZY Z. Okay. So I'm not going to wait unless somebody wants to unmute, but probably in the meantime, you computed that this is Z plus Z is equals to identity times 2, while this is equals to X minus X is equals to 0, and this is also equals to 0. And if we compare with this Schur's lemma setting here, so I could also divide by the dimension here, then I would be removing this factor 1/2. Okay. But you see, we have a weird situation where delta of Z is equals to not identity, but Z times 2. I will erase. Sorry, I'm a bit here. Okay. 2 times Z. So we have this, and it's neither 0 nor identity. Okay. So what's going on here? And the thing to note is that basically we are not working with irreps. And if I understood Markus correctly, we have two kinds of irreps. So conjugating by Z in this way, the way we do, is a representation of this Z2 group, which is maybe isomorphic to not 0, but -1 to power 0 and -1 to power 1, which is simply 0 and 1. Yeah. And now, what is our group representation? And we didn't mention that we are discussing an adjoint representation. So in this case, we want to say that, for example, we want to conjugate the matrix A by Z. That's our adjoint conjugation. And now we can look at those cases here, and we see that we have 4 cases. If I have identity, that will get conjugated by z to what? To z squared. Yeah, and this is what? This is identity. Then we have z, and this gets conjugated to z to power 3. And using this equation, we get that this is z. Okay. Then we have the conjugation of x, which is z x z. And this is what? This is minus xz squared, previous line. This is minus x. And then we have y, which is conjugating z, y, z. And this is minus y. So what do we get is that if I conjugate by the z matrix, those 4 matrices move to -1 to some factor phi of my matrix, and I have my matrix A, roughly speaking. Okay. So, and this phi A is 0, is from the set 0 or 1. So in that way, we get this representation of this Z2 group. It's just a phase. It's Z2 is basically in physics sign. So if you have the Ising model is Pauli Z operators acting at maybe neighboring sites. So we say that this Hamiltonian has a Z2 symmetry, because if we take Zi and define it to be Zi with a minus, then H goes to H, because this -1 go. You get minus here, and -1 squared is 1. So the Hamiltonian is invariant under flipping the sign of all z's at the same time. So there's this kind of nomenclature in physics that the Hamiltonian has a certain symmetry. And here I wrote down the representation of the symmetry, which means I'm flipping the z, but my Hamiltonian is symmetric. So here we have something similar. If we are flipping with z through this adjoint representation, then identity and z stay invariant, but x and y change with a -1. So now we can, in some way, this is equivalent to counting irreps, and basically these will be irreps with +1 sign, and this will be irreps with -1. That's roughly this. Okay. So long story short, I'm probably not working out this example in full detail, but you get the idea that there's a splitting of +-1. And the last thing to say is that in general, if we don't have irreps and we average over a group that is splitting into irreps, let's say the group G gives rise to a set of lambdas, which are those irreducible representations, irreps. Okay. So please check on Wikipedia the definitions, because yeah, that would be maybe another half an hour to discuss this. But basically, you can split into different blocks. And when we are averaging over this larger group, which is splitting into irreps, so let's say we have GAG -1, let's say. And then this is the sum over lambdas. And here we can write a projector onto this irrep lambda. Okay, so this is a slightly different formula than I was saying. But now, if I understood Markus correctly, we have two plus 1 irreps, and we have 2 times, well, this is terrible. Let's say we are indexing irrep index, and we are indexing it by +1 and -1. And then here we have multiplicity. And we have here 2 and 2. Okay. So long story short, basically, our dephasing channel. Where do we have the dephasing channel? This dephasing channel arises not so much as the Schur's lemma, but it arises more as projectors onto irreps. So we can project onto the +1 subspace and the -1 subspace. Yeah. And because those projectors might be giving some zeros, then we get a 0. And sometimes they might be, a projector might not be doing anything to this. So that's why we can get that this is 2 times z, which is what we are feeding in here. While here I should either get 0 or identity. But we are not working with an irrep, we are working with a group average which splits into irreps, and then we have this summation over those projectors. So the way to see it is that we have a big matrix A, and then after the group average G over G, we get that this matrix, it was a full matrix. Now this matrix is splitting into some blocks where you have zeros here, and then here you have pi lambda of A pi lambda, and here you have pi lambda prime A pi lambda prime. Okay, so this is this kind of situation where it can split into some sort of blocks. Yeah, so it is still removing some stuff. It's twirling away, you say sometimes in some jargon, but it's not collapsing it onto an identity. And to collapse something on the identity, you either have to have irreps with multiplicity 1 and very simple stuff, or just a single irrep. Then you have this identity over the trace of A. So just a simple matrix here where there's nothing going on. Yeah.
So I'm not sure, like, I don't understand how you get the identity. Like, if you already have an irrep, you have no lambda to sum over, and pi lambda is just the identity.
Yeah, so this is maybe a bit different than it's related to Schur's lemma, but this is maybe not exactly the same. So you're saying, let's say G is already an irreducible representation, so you cannot reduce that group G further. So then here we should have a projector of A onto lambda.
So let's say G is just ±1, the Z2 group, and then G -1 would be also ±1, and the adjoint will just give you the identity to a one-dimensional, like, scalar numbers, right?
Yeah, this is a good question. I think I still don't understand the full thing fully. So what you said with those identities, I'm not sure. I think exactly the thing was that those irreps are kind of so one thing in group theory is that you can have a trivial representation in the sense that you have essentially only one element or something like this, right? And so all those irreps are kind of inequivalent. So we have kind of 4 of them. But how do you get the projectors now? Yeah, this maybe I still need to ask
So-
somebody.
When we are talking about like Schur's lemma, the corollary of Schur's lemma that give us the identity, what was the like additional assumption we need?
So the Schur's lemma is this kind of, this is averaging over a group, and if that group is already an irreducible representation, then we have this kind of situation, zero identity. Yeah.
So we just need the representation to be irreducible.
So then in our case, when we were discussing this adjoint representation by ZAZ, this is reducible. And I was discussing what happens if you apply it to different matrices, and you see you can get this the same matrix with a +1 sign, and the same matrix with a -1 sign. And so we get multiplicity 2, I think, here, and here also multiplicity here 2. But if we are summing here over this adjoint over this adjoint action of this Z2 group, in that representation is reducible, and we should effectively get this kind of projector into the game. But wait, maybe we have it. No, the dephasing channel of matrix A would be matrix A plus Z A Z, which is just summing over those two adjoint representation. Either we are doing nothing, or we are adjoining by Z. And now we can do this projector onto irreps. So, and this is more or less some sort of lemma, I think, yeah? This is not obviously the same derivation here. But I could project A onto this identity representation, plus I could try to project onto the Z representation this A, and I think we can do this with this -x, I minus x or something. So
What is -x?
wait, now I'm thinking. I think those will be going to 0, but basically the idea is that we can write A as A plus bx plus c y plus d z, and basically those projectors should pick up this and this. So the dephasing of A should give me A identity plus dz. And I just don't know now exactly which kind of projectors we need to consider, but you're kind of considering projectors pi z, which leave invariant this, and everything else they project to 0. I think that's more or less how that would be working.
I think like the space is really just like it'll decompose in the computational basis, because 0 state is invariant on the any action of the group, like either identity or Z, and 1 state it will be 0 and -1. So like you have this
Right. So you're saying this? Z0 is 0?
yeah, so like you have this decomposition where the 0, 0 part is identity for both of the group elements, and 1, 1 operator part is +/-1 for those elements. So it's like one direct sum plus minus one, right?
So you're saying that my P lambda projector should be maybe 0, 0?
Yeah. And 1, 1.
So so P pi plus 1 and pi minus 1 should be 1, 1. Okay. Let's see. So I'm taking a matrix and I'm averaging over this kind of Z2 group, and let's see. 0, 0, A 0, 0 would be the formula, yeah? Plus 1, 1, A 1, 1. Okay, and now next I'm putting this in. And wait, before I do this, maybe just to explain that this decomposition always holds for 2 by 2 matrices. You can always write this as A plus D, A minus D, and then B plus D minus IC, B plus IC. And we assume that our A is Hermitian. Yeah, that's how we find A, B, C, D. So there's, I think we will cover in another tutorial Hilbert-Schmidt. Scalar product for matrices, which induces the 2 norm. But for the 2 by 2 case, you can do it by hand, yeah? So now I'm going to use this. So identity will not do anything. So if I put in identity here, I will get those projectors collapsing. So A will be 0, 0 plus 1, 1. Okay. And that will give me an identity again. Now, if I put in X here, then X on 0 gives me 1, the 1 state. It flips the bit. Once I flip the bit, I will have here 0, 0, 1, 1, 1, 0. Yeah, because I flipped the bit here. So this becomes 0. So basically the B and C component, which is X operator and Y operator, will be 0. And then I will have plus D. And I will have 0, 0, Z acting on 0, 0, plus 1, 1, Z 1, 1, yeah? And so those projectors, Jean-Greg, that you proposed, they are working, no? Because I'm getting A identity, and then I have 0, 0. I hope that works, right?
Yeah,
I get
so this identity Z representation is reducible and it is like decomposable as a direct sum of trivial representation acting on the 0, 0 space and plus minus 1 representation acting on the 1, 1 space. That's how I understand.
Yeah. That's nice. Okay. Plus DZ, right? So this is exactly what we were supposed to get, and you got it using your projectors, right? So it seems that this is working that way. So what I'm messing up in the presentation here is a little bit to very clearly say what it means to have an irrep, what it means to see what are the projectors and so on. But I think with this we are more or less in game, right? I think the next step would be to anybody who wants to do it more carefully to look at those definitions of irreps and look at the definitions of a joint representation on Wikipedia, and then try to see how to build those projectors the way John did. No? And then you have a full picture. In this moment, I'm like just trying to follow and get the more or less right result. Yeah. So what we achieved here is to discuss a more general formula that appears in physics quite often, actually. I never use it myself, so that's why I'm not very familiar with it. But we get this intuition that we have a full matrix, and then it splits into blocks. And the splitting into the blocks is done by implemented by those projectors here. Okay. And we had this weird situation that that you either get 0 or 1 because delta of z is again z. Yeah. And so the link was to say that we are making projectors, and one of those projectors on z will give us again z, and that's why we get this z. And the projectors that we constructed here is explicit in 2 dimensions, so that worked out, no? So we were supposed to get this result, but here we were doing the projection, and we got the same result. So we kind of are maybe happy with this formula by this example. That's how to use it. It's a very weird smiley face, but let's say we are happy. Okay, good. Let's maybe finish this discussion here.